All right, so we're going to try to get these to the mixture enthalpy form. So we're going to have 0 equals the m dot 1 of our H, so our saturated liquid, minus m dot 2 over the saturated liquid at state 2, plus, and so we'll have m dot A out front because we want to get to the humidity ratios, and that's going to be multiply our quantity of HA plus the humidity ratio times the enthalpy. It's going to be the saturated vapor value at state 3 minus the enthalpy of air plus the humidity ratio at state 4 times the saturated vapor value, all at state 4 there. All right, so that's our energy equation, and we'll label that actually number 2. So combining number 1 and 2, we get, and you can go back to check, the equation 1 was the mass equation that we had solved for the mass flow rate of 2. But when we make that substitution here, we get the mass flow rate of 1 times the quantity of the saturated liquid enthalpy at temperature at 1 minus the saturated liquid enthalpy at temperature 2 plus the mass flow rate of the air times the quantity of a big long thing here. So we get the enthalpy of the air at state 3 minus the enthalpy of the air at state 4 plus the humidity ratio at state 3 times the saturated vapor value at state 3 minus the humidity ratio at state 4 times the saturated vapor value at state 4 minus the quantity of our humidity ratio at state 3 minus the humidity ratio at state 4. And all that times the saturated liquid value at temperature at state 2. All right. So now we just need to put all those values in together. Well, put all those values in. But first of all, we're going to solve, well, what don't we know here? So what we actually did in that process, when we substituted, when we brought 1 in, equation 1 in, and substituted 2, basically we substituted in for the mass flow rate of 2. Now, the reason we did that is because we know the mass flow rate of 1. We don't know, that's all what we're trying to find is the mass flow rate of 2. We don't know the mass flow rate of the air either. But with the mass equation, we can substitute in for the mass flow rate of 2. And now we can solve for the mass flow rate of air. So that's what we're going to do next. We're just going to solve this equation for the mass flow rate of air and find out what that is. And then we can come back and use equation 1 to solve for the mass flow rate of 2. All right, so that's our strategy going here. So the mass flow rate of the air is equal to the mass flow rate at state 1 times the saturated liquid value, temperature at T1, minus the saturated liquid value at T2. All that divided by, you got the enthalpy of the air at state 3 minus the enthalpy of air at state 4, plus the humidity ratio at state 3 times the saturated vapor value at state 3, minus the humidity ratio at state 4 times the enthalpy of the saturated vapor at state 4, minus the humidity ratio at state 3 minus the humidity ratio at state 4, times the saturated liquid value at state 2. All right, and as always with our enthalpy as the air, we're going to use our Cp of the air times our delta T, T3 minus T4 there. Now what else do we need to find here? Actually, going back to the numerator, m dot 1, we're given that. So we know that we can find these values. We can find actually all the H values. So we got to find omega 3 and omega 4. So that's where we can go to the chart and look those up. So let's look up omega 3 first. So the humidity ratio at state 3. So to find humidity ratio at state 3, we use figure A-9, and we're English units with the Fahrenheit, so we'll use that. We also need, at state 3, we got our temperature at 3, which is 50 degrees Fahrenheit, and we have the wet bulb temperature of 35 degrees Fahrenheit. All right, so with that, we should be able to find omega 3. And also, we can find omega 4. So we're going to use figure A-9E as well. And there we have the humidity ratio, or relative humidity is equal to 100%. So we know where that curve is, so that should be pretty easy. And we have the temperature there as well, is 120 degrees Fahrenheit. Therefore, omega 4 is equal to. All right, so let's go to the chart and get those values. All right, so for omega 3, we were told we had 50 degrees for the dry bulb, and we had 35 degrees for the wet bulb. So those are going to cross right there. Right, and if we follow that across, my dashed lines hopefully stay in the right spot here as we go. Yeah, we're right there, right? So we're right on the spot there of 0.001. All right, so that looks good there. And then for our second case, I'll do this in blue here. We were told the 100% relative humidity, so we're on this line out here, and the temperature was 120 degrees Fahrenheit. So we're up here, and all right, if I file this up here, I never hit that line. Yeah, so what happens here, we can't use the chart to get omega 4, so we'll have to actually calculate that out. So let's go back and do that. All right, so we found from the chart that omega 3 is equal to 0.001. All right, so that worked out well. Omega 4, we actually cannot use the table. So we didn't do that. So instead, we're going to calculate that out using omega 4 equal to our 0.622 times we had the partial pressure of the vapor divided by the mixture pressure minus the partial pressure of the vapor. Now, at state 4, we did say that it was 100% relative humidity. So being 100% relative humidity, the partial pressure of the vapor at state 4 is saturation pressure. All right, so now it's the mixture pressure minus the saturation pressure at the mixture temperature. All right, and so that temperature is T4. All right, the saturation pressure at T4. And if we look that up, we'll find that we get 0.622 times that pressure, which is 1.695. And we'll have 14.7 minus 1.695. That's all in PSI, and it's all going to cancel out, so I'm not adding PSI right here. But we'll get there for omega 4 is 0.1303 for our humidity ratio. All right, so now we can plug all our values in, and I'll do that on the next slide. All right, so I copied over the equation that we're going to plug our values into, and then I looked up our values here that we're going to plug in. So let's write this all out. So we got the mass flow rate of our air is equal to the mass flow rate at state 1, so that's our 100,000 pounds per hour, multiplied by our 38.09 minus 97.98, and those are all BTUs per pound, divided by 0.24 BTUs per pound degree Rankine, and we got our temperature difference at T3 50 minus T4 at 120. That's degrees Fahrenheit, and it's going to cancel with degrees Rankine because it's the same interval as we're looking at the difference. And 0.001 for our humidity ratio at state 3 times 1083, 83.3 BTUs per pound minus our 0.1303 times 1,113.5 BTUs per pound plus, go on the next line here, we got our omega 3 minus omega 4, so 0.001 minus our 0.1303 times our 38.09 BTUs per pound. All right, so there we calculate that out. We get our mass flow rate of air. It comes out to be 38,420 pounds of air per hour. So now if we substitute this back into our equation 1, which was our mass flow rate at 2 is equal to mass flow rate at 1 plus the mass flow rate of the air, which we just found, times the humidity ratio at 3 minus humidity ratio at 4, we get the mass flow rate at 2 is equal to our 100,000 pounds per hour plus our 38,420 pounds per hour times humidity ratio at 3, our 0.001 minus 0.1303, and we come up with 95,032 pounds per hour. Very good. Okay, so we were able to do that mainly with calculations, but now I want to show you one other way where we could do this with the chart, but it's, again, you want to be very careful when you do it this way. So we'll start that on the next slide.